Hey mathematicians, we are wrapping up the linear systems unit. In this lesson, I want to cover methods for solving systems and types of solutions. So let's start with methods for solving systems. We learned 3 different methods: graphing, substitution, and elimination. But how do we know when to choose which method for solving? So let's start with graphing. The best time to use graphing is when your equations are already in slope-intercept form for graphing. The other thing to keep in mind when using the graphing method is you need to be okay with the level of accuracy that graphing provides. So if you just need an approximation, graphing is great. So let's write an example of when both of the lines are already in slope-intercept form. For example, if the first equation was y equals 2x plus 4, and the second equation was y equals negative 1/2 x minus 2. Both in slope-intercept form, and if an approximate solution is okay for you, then graphing is a great option. Now, for the substitution method, the best time to use the substitution method is when at least one equation has already been solved for x or y. So that's just going to save you a step. You don't have to solve for x or y. For example, if we have the first equation is x equals 3y plus 1, and the second equation is not solved, but at least we have about an expression for x to plug into the second equation. That would be a great option for substitution. And finally, we have elimination. And the best time to use elimination is when both equations are in standard form. And this way, you can line up all of your terms for quick elimination. For example, if we had negative 2x plus 4y equals 5 and 2x plus y equals 10. Not only are these two equations both in standard form, but they're all ready for elimination. We don't even have to do any multiplying. We already have inverses of the x terms. So that would be a great example of when to choose elimination as your solving method for this system. Let's look at a few more examples just so that we can make this perfectly clear. So, for example, if I had y equals 3x and y equals x minus 4 as a system, graphing would be a great solution because these are both already in slope-intercept form and ready to graph. If an approximate solution is okay with me, if I don't need to be totally precise, then graphing would be great. So more examples that would be good candidates for using graphing would be y equals negative x plus 4 and y equals x plus 4. Y equals 2x minus 6 and y equals x minus 1. So what happens if an approximate solution is not okay? Well, one thing you can notice about these systems that are already set up well for graphing because they're in slope-intercept form is that they're also already solved for y in both equations. So if graphing is not a good option for you, then substitution would work really well for these. So if an approximation is not okay, then use substitution. And let's look at a few more examples for substitution. So what if we had one that was in slope-intercept form, and then the other one was solved for x? That would be a great one to use for substitution. Graphing isn't always the easiest way to go, so the substitution method would be a lot more efficient in this case. Another example would be x equals y minus 3 and 5x plus 3y equals 1. Or y equals negative 2x minus 9 and 6x minus 5y equals negative 19. These are all great systems to use the substitution method with. Now remember, we're just looking at the most efficient method to use. You could absolutely change this equation into slope-intercept form and then graph this system. Or you could change this equation into standard form and you could use the elimination method. It's really up to you, but you do need to understand what is the most efficient method, and that's what we're talking about now. Okay, so finally we have the elimination method, and for the elimination method, we're looking for systems where both equations are already in standard form. So here's a good candidate for using elimination, and here's another good candidate. And one more example. Negative 2x plus y equals negative 17. Okay, so make sure you've taken notes on the previous slide. You have a handout that looks exactly like this. Make sure you take down when to use each of these methods for solving a system. Okay, I want to move on to the types of systems and how to identify the type of system that you have based on the graph that you have, or based on the equations of the lines, or based on what's happening in your solving process. Let's look first at intersecting lines, and I want you to take out your note sheet that looks like that previous page and make sure to follow along taking good notes. So the first type of system is a system of two intersecting lines, okay? And we know that these lines will share exactly one solution at their intersection point. One solution. And any two lines will intersect if they have different slopes. Even if the slopes are just a little bit different, these lines will eventually intersect at some point and have one solution. So what would that look like? Well, that's pretty easy. We can just do 2x plus 5, and any other slope here is going to work. So a slope of 1 would work. These two lines, this one has a slope of negative 2, this one has a slope of 1. Since they have different slopes, they will eventually intersect and have one solution. And it's really a good idea, despite or regardless of what type of method you're going to use to solve your system, to at some point, either before or after you solve the system, always put it in slope-intercept form as a check, because then you can quickly check the slope and y-intercept and see what type of system you have. And in this case, we would know, since the slopes are different, we should have one solution for our system. Okay, so finally, the outcomes when you solve these types of equations. Well, you're going to get x equals some number like 5 and y equals some number like 0. So you come up with an ordered pair, 5, 0. Okay, let's take a look at parallel lines. So we know by looking at a graph that these two parallel lines are never going to meet, and therefore they will share no solutions. So the system has no solution. And we can tell that when we look at the equations, because the slope of two lines that have no solution will be the same. We'll have the same slope, but it will have different y-intercepts. Different y-intercepts. And so what would equations that are parallel look like? Well, they might have a slope of 1/2 x plus 5. And the second line would have to have the same slope, but a different y-intercept. And when we solve this system, we won't get an x equals a number and y equals a number like we did for the one solution systems, but we will get an untrue statement. So when we're solving, if we get something like 0 equals 4 or negative 2 equals positive 2, we know, or we have at least a good indication that we're looking at no solution, and we need to find some way of double checking. One way of double checking would be to be putting those lines both in slope-intercept form and see if we have the same slope but different y-intercepts. If that's the case, then we know we have two parallel lines. They'll never share a point, and so the system would have no solution. Okay, moving on to our last type of system, coinciding lines. You can think of coinciding lines as two lines that lie right on top of each other, but they'll have the same equation because they're really just the same line. But we think of them as two lines lying on top of each other. So since they lie right on top of each other, they will share every single point, and they will have infinitely many solutions. So since they're the same line, their slopes and y-intercepts will be the same. And what will the equations of the same line look like? Well, you would think they would look exactly the same. And you'd be right in a sense. You just need to be careful. So if the first line has an equation y equals negative 3x plus 2, your second line might look something like this. And it's not immediately apparent that this is the same line. However, if you were to change this second line into slope-intercept form by subtracting 3x from both sides, you would quickly see that y is equal to negative 3x plus 2. And it is, in fact, the same as the first line. And what kind of outcomes will we see when we solve a system like this algebraically? So what we're going to get are true statements without a variable because the variable has been eliminated. True statement, I can just barely squeeze it on there. So you may get something like 0 equals 0 or 8 equals 8. But if you have a true statement with no variable in that statement, that's a great indicator that you're looking at coinciding lines in a system that has infinitely many solutions. So at that point, you would want to put your equations both in slope-intercept form and check to see if you have the same line. All right, let's quickly review. Going back to our very first topic, we looked at the different methods for solving systems of equations. The first method is graphing, and for graphing to be the most efficient method, you first want to make sure that both lines are in slope-intercept form. For substitution, you want to make sure that at least one equation has already been solved for x or y to save you that extra step in solving. And finally, for elimination, both equations should be in standard form, and it really helps if one of the coefficients at least have the inverse values. So in this case, it's negative 2x and positive 2x. When I add these together, I will immediately eliminate the x terms. Then we looked at the three different types of solutions that you can get with a system of linear equations. The first one is intersecting lines, which would have one solution. You're just looking for different slopes here, and the outcomes when you solve these are x equals some number and y equals some number. And then the two sort of special cases are parallel lines and coinciding lines. Parallel lines will never touch. Those two lines will never share a point. So the system has no solution, no shared points. And we're looking here for same slope, but different y-intercepts. And that's sort of the definition of a parallel line. And you can find that when you put the lines in slope-intercept form, you can make sure that they have the same slope and different y-intercepts. And when you solve algebraically, you're looking to get an untrue statement like 0 equals 4. Finally, we have two coinciding lines. These will give you infinitely many solutions. These two lines share every single point. They will have the same slope and the same y-intercept because they are virtually the same line. And if you put both of the equations in slope-intercept form, you will see that they have the same slope and the same y-intercept. When you solve algebraically, you will be getting true statements without a variable like 0 equals 0 or 8 equals 8. So that's it. A lot of this will be on the test, so make sure you've taken good notes and make sure you revisit those notes. Go back, make sense of them, revise them, summarize them. And we will practice a little bit more of this in class. See you then.